No.
No Catherine.
No Tristan.
Cook.
Cook is here. I got Cook.
Not here.
Well, for this year though, that counts as being here.
He's in the phone.
He's with us. With our thoughts.
He's on the computer, but his is mine here.
I haven't seen Tristan in like forever.
Yeah.
Is he been in school at all?
Not really.
Okay. Well, who is the other? Roxanne? Not Roxanne. Catherine.
To get to school, you gotta get off early. Tristan doesn't get off.
Okay. Let's see how I can muddle my way through this. All right. So here is what we're going to do today. So hopefully you've gotten 5.2 through in the rearview mirror now, and you're working on 5.3 a little bit, right? And the biggest thing in 5.3, the thing I gave you already was so this is going to be the first part of the fundamental theorem of calculus. I gave you the second part of the fundamental theorem of calculus. They like to call it FTC for fundamental theorem of calculus, right? It gets its own little acronym, or that's the right word, yes. Okay. So you on what day was that? When did we talk about this? When's the last time we had class? Friday?
That sounds right.
Okay. So whenever we last were in class together, I gave you the second part of the fundamental theorem of calculus and said, hey, if f is a continuous function on some closed interval ab, we can find the value of the integral from a to b of f of x dx by simply finding a antiderivative of f and evaluating it at b and a and subtracting those. And if we do that really simple process, we can get the area between the x-axis and the curve from a to b, right? I mean, it just sounds like it's just like, really? That's it? That's all I got to do? Find an antiderivative, which is not hard, right? Here's a function. Here's an antiderivative, right? I'm betting I could plug a number in two different numbers in there and subtract them, right? Yeah. So I mean, so if you're in the middle of 5.3, that's literally what you have to do, right? To find the value. Yes. Everybody got there? No. No. No.
Not quite.
Ryan?
Yay! We're all in the same fog.
Jackson. All right. Now, if you're not totally brain dead at this point, you should be really wondering to yourself, how could this possibly work? How can I take an antiderivative of a function, plug some numbers into it, and actually get the area that's underneath the curve between it, right? I mean, you could be in the whole awe thing, right? It's like magic, right? David Copperfield, or I don't know, who's your favorite magician?
James Franco.
He's a magician. I thought he was an actor.
He was on
Keller.
He was on, what was it? America's Got Talent or something for magic.
Okay.
Franco, like from Spider-Man?
I think so.
Yeah. Well, I mean,
Same guy.
that's the James Franco I know,
Yeah.
but I do believe I've heard that he does dabble with.
Yeah. He was on America's Got Talent.
Well, anyway, so you should be wanting to pull back the curtain and see what's going on here, right? You should be like, ooh, well, at least for a little while you can do that, right? Okay, good. All right. So we'll come back to this because at some point I need to prove this, and I'll probably end up doing this proof as a separate video and putting it out there, so that Brooke has something to watch after she watches the review video, right? She's got a little popcorn left over. She can throw in a good 15-minute Mr. Schultz video after the hour of reviewing calculus, right? Sounds like a great Saturday evening. Anyway, let's go back though. The bottom line is I can't prove the second part without the first part. That's really what it comes down to. Yes. Yeah. So so there's no point even talking about proving it until we talk about the first part of the fundamental theorem of calculus. And I'm not even going to talk about the first part of the fundamental theorem of calculus. I'm just going to give you a problem, a situation, right? So here's a function f, and I know f is continuous on AB, right? Okay. Yep. Nice continuous function there. And I marked off the interval a to b, right? And what I'm going to do is I'm going to start by going through and saying, hey, what if I wanted to find the area under the curve for different pieces of this, right? Instead of doing the whole thing, right? I know if I want to do the whole thing, I just do the integral from a to b of f of x dx, and I get the whole area, right? Okay. So I'm going to take this thing, and I'm going to break her up into little subintervals. So I'm going to go put one in here. Let's see what color I want this to be. Let's go black. No, black won't work.
You do purple.
Hey, Catherine. She's here in spirit, right? Okay,
Yeah.
so if I go through and do this, I'm gonna go through and say, okay, I'm gonna put in an interval here, right? And obviously that's between A and B and it has a value. For right now, I'm gonna call that little b sub 1. And if I wanted to, I could go out here someplace else and put in another one and call this little b sub 2. How many do I want? Let's do another one out here and call this b sub 3. And then I'm going to do another one out here that I don't know exactly where I want to put it, right? I'm confused. I'm going to say out here somewhere, there's one I'm going to call b sub x. Because obviously 1, 2, 3 are my x values, right? Okay, so there's numbers for x on it there, right? Okay. So if I wanted to go through and find the area, could I find the area of just this first one? So the area going from here to here. Let's call that big B sub 1. So if I wanted to find that area, how would I do that? Get rid of this. So if I wanted to find the area that is big B sub 1, what would I have to do?
You'd have to find delta x.
Okay, not the actual, I mean, how would I express the area? You said something, I know what you
I
said.
was gonna say.
Okay, you're getting way too technical on it. Yeah, that's how you're going to do it. That's how you're going to do it. But literally, how do I write the area? How do I find the area between the x-axis and the curve? The area under the curve from A to B sub 1. Jordan! You're like, all I'm asking you to do is how are you going to get the quick trip? I want you to tell me drive the car. And you're explaining to me, put the key in the slot, put on your seatbelt, put your blinker on.
You gotta make sure you're safe when you're going to quick.
I don't need all those details. What were you going to say, Jordan? No, I'm going to do an integral.
Yeah,
I'm going to do an integral from what?
from A to B sub 1.
There you go.
Yes.
Of
you
what?
did.
Of f of x dx. And if I could find that integral, yes, by doing this, this, and that, if I could find that integral, then yes, I would have the amount of area there, right? Okay. And just for, so if I did this definite integral, it will give me a number. In fact, what kind of a number would it give me in this picture? What does it have to be?
A positive.
Positive number. So I'm going to give it a positive number, but just because I know it's a number, I have no idea what it is, but let's just call it 1, right? So the area from A to B sub 1, the area of this piece is 1 unit, right? Okay, the number is not important other than we know it's going to be a definite integral always gives me a number, right? Okay, so could I now go through and I don't know at this point. How would I go through and find the area from here to this one? So this region here, let's call that big B2. How would I find the area that is big B2?
Well, you do the same thing, except instead of going to B1, you go to B sub 2.
Yep.
Then you'd also have to, you have to subtract out the area.
Well, I want this whole area, right?
Okay, if you want the
Okay.
whole area.
And it's going to be a number, and by looking at my picture, the number has to be bigger than 1. 1. So let's just pick a number bigger than 1.
1.5.
1.5. There we go. Definitely bigger than 1. The number doesn't matter, other than that we're not finding just this one little piece. We're finding the area of this whole piece, and whatever it is, it's got to be bigger than that, right? Because it's positive area, right? The graph went below. That's a different story. Yes. Okay. So starting to see how this game is played. So we should be able to even more quickly now find the one that would be the area from here over to here. That would be big B sub 3, which would be the integral from what?
A to B3.
F of x dx. And that would give me another number that has to be even bigger than 1.5 because we added more area to it, right?
100.
Okay, not that much area.
You don't know that.
They're not all the same, so let's make this one like 2.1, right? Okay. I don't give the idea that I'm adding the same amount of area all the time because obviously I have no clue. I don't know what the function is, right? I just want you to understand that when I do a definite integral, I get a number all the time. That's why the calculator can do a definite integral for you, right? It'll actually find the value of that area if you do the function, yes? All right, so what we need to get to then is, okay, remember this one here? I didn't know where I wanted to put it, so I called that b sub x, right? Okay, so I want to find the area from my starting point all the way to wherever that line is. Well, that would be big B sub x, right? The area to wherever that is. And could I write an integral for that? Yeah, it would be b sub x, and that would be the integral from a to what? B sub x of f of x dx. And at this point, it would be a number, but I have no clue what that number would be. Right? All right. So basically, what am I doing? I'm finding area up to a given point. But I can choose any point I want in this interval. Right? Okay? Those are values for x. Okay? So if I wanted to now, just to change this just a little bit, could I put this as a specific number? Let's say, I mean, I know this isn't 0, so let's make this, let's say that the interval goes from 0.5 to 4. That's my AV, right? I don't care what that number is. I just need it not to be 0 because, Lauren, when I drew my picture, A is obviously not at 0. And you'd be like, Mr. Schultz, that's not 0, right? Which you'd be right, yes? Okay. So if my interval went from 1/2 to 4, could this be a 1? Could this be a 2? Could this be a 3? Yeah, I mean, I'm picking values for x, right? Okay. Yeah. I mean, not necessarily drawing a scale, right? But those could be some value for x, right? So if this was 1, this was 2, this was 3, then this one would be what? X, whatever value you want to be, right? Okay. Now this is the part where you're going to hate me because I'm now going to change what I just wrote there, right? Because I'm going to go over here now and say, okay, could I do this instead of putting this as b sub 1? Could I go through now and change this to 1? Because I know b sub 1 is 1, right? Yeah. Okay. So I could go through there. Am I going to get my purple back? Come on. There you go. So I could go through and do this 1, right? Okay. So then what would this one have to be changed to?
2.
Hey, getting the idea, yes? Okay. Let's see. I'm going to just go through and erase these right now because I know what's going to happen here. Okay. So then, where is it there? Boom, boom, boom. So then this is going to be 2. This one's going to be 3. What's this one going to be? What would I have to put there? I'd have to put x there. But there's a problem. Is this x the same as the x that's going into that function?
No.
Well, yes and no, right? I mean, to get this graph, right? I mean, Ryan, to get this graph, I had to put x values in and get the actual value of the function, right? But the value I'm putting in the function doesn't have to be the same x value I have down here. It has to be in the same interval, right? I have the same choices, but at the same time, are they the same x? The answer is no, right? Okay. I mean, if they were, I'd have to leave this like this, but it's not, right? So what I have to do is I'm going to introduce what they call a dummy variable. Basically, instead of calling it x along this axis for my graph purposes, right? I'm going to say that this is going to be the t-axis, and my numbers go from, my interval goes from 0.5 to 4 on the t-axis, and then somewhere in there, these are these x values, right? Right? They're still there, right? Only thing that's going to do is instead of calling this just plain f, I'm now going to call it what? F of t. What does that allow me to do over here then? Well, now I can go through, and again, bear with me here, but I can now get rid of all of these x's and put 1 here instead. There you go. And does that fix my problem that I had down here? Yeah, because now when I go through and do this, I could do that more, I suppose. So now this is going to be f of t dt, f of t dt, f of t dt, and an f of t dt, right? Okay. So now it's not confusing, right? This t is going to give me the graph. X is where on that interval I want to find the area up to, right? With me so far, right? Okay, so every time I do one of these integrals, I'm going to get a different number, right? But for each one of those values I choose, whether it's 1, 2, 3, or any value x, is it only going to give me one specific area? My question is it a function?
Yeah.
Well, if it's a function, okay, wow, this is where you're really, you know, it's like if you weren't playing on, it's like, did anybody actually watch? I posted the video that I did last spring. And I did this on my whiteboard at home. So all I had to do with my fingers is just wipe off the whiteboard. Yeah. Ryan, did you watch? No. Okay. So, you know, so obviously here I can still do it. But now I'm going to say, hey, this is really a function. So if it's a function, can I use function notation instead? Sure. What can I call this? Where's my purple again? I could call this B, big B of 1. This one would be big B of 2. This would be big B of 3. And then this would be big B of x. Okay? And what is this function B doing? It's giving me the area under the curve from some starting point to wherever x is, right? Okay? So function B is keeping track of those areas, yes? Okay? Well, in the end, they're like, why am I calling this B? That's silly, right? B for Brooke, right? Might as well be. I keep getting confused. I'm pulling out all my old physics tests, and I have a bunch of these physics tests, and they all have Brooke B on them. Yeah, it's like, how did you do physics twice? It's like, okay, wait, no, it's wrong Brooke. Anyway, why are we calling this B of x? I mean, why am I calling it B? Because I called these little numbers down here B. Why did I call these B? Because I knew the end of the interval was B, and I was changing the end of the interval, basically, right? You know, that's where those little B's come from. But do we really need to call the function B of x? No. So in the end, what they're going to say is this function B of x is finding out the area from the starting point to any of those places, and that is a function. Okay? So they're going to say instead of calling it B of x, we're going to call it G of x. And G of x is going to be the function that takes the area from the starting point A to some value of x of our function f of t dt. And I need you to understand that this is a function. For any value I put in for x, I'm going to get a specific area. And if I graph it, I'm going to get a graph. Right? It's going to give me the area, and, you know, for up to 1, 2. I could even put it, you know, if I wanted to, could I put it on 1.5? And it would give me the area to 1.5. Absolutely. Yes, Jordan. Well, that the f of t is just going to be the equation of the function, right? So if it's x squared, it'll be t squared. If it's a sine, it'll be sine of t, right? And you'll see, like, you know, here I use t, but a lot of times when we're doing sine and cosine, we'll do theta as our dummy variable. Z, u, it doesn't matter. It's just a variable to keep track of the graph itself, right? But this variable here is really important because this tells me where I'm taking the area up to, right? But it is a function, right? G of x would have all the things that would be true about any other function, right? It's going to be, for each domain value, there's exactly one range value, et cetera, okay? Okay. That is not the fundamental theorem of calculus part 1. That is the setup to understand that we can create a function that is integral defined, right? This function g is defined by this integral. And I need you to understand what that integral is doing. It's finding the area up to some value x. Okay? Okay? All right. So what does the fundamental theorem of calculus part 1 actually really say? It says if f is a continuous function on a closed interval ab, okay, and we define g to be this function where x has to fall somewhere between a and b. I didn't say that up above, but obviously the picture gets all messed up if x isn't between those two values, right? All of a sudden, Riley, I'm out in the pasture, right? Instead of, you know, it doesn't work, yes? So if I, but now you understand. I mean, if I've just thrown this at you without anything up there, you'd be like, what the heck is this? Why are we just setting g of x equal to the integral, right? Well, this is a very specific way we defined it, right? Okay, so we have f as a continuous function. We have g of x defined this way, as long as x is between a and b. What can we say about g is really what it comes down to. So g of x is a function, and there are three things that we can say about g. The first thing we can say is that g of x is blank on this interval, it is blank on that open interval, and then we can say something about g prime of x. Okay. If you're significantly clever, you should figure out what's going in those first two blanks, because you've seen this over and over again. Okay, so what do I know about this function here? F is continuous on this interval, right? So if I'm finding all those areas underneath that curve, what kind of a function am I going to get between A and B when I look at all those different areas? Is it going to jump, like go from this one to this one, or is it going to be a nice smooth, get every value between them? It's going to be nice and smooth, right? So how we do that? We're going to say that that function g is going to be what? Is going to be continuous on the closed interval, meaning that there's not going to be a spot where I can't find an area. And that makes sense, right? If the graph is continuous itself, no holes or jumps or anything right here, no discontinuities, you're going to get a nice smooth curve when you do the areas, right? Okay. So that one's pretty obvious. G has to be continuous on this closed interval. What else is G going to be? Differentiable. But when we talk about differential, we don't differentiate at endpoints, do we? Because we don't know what's happening. Remember, we can't have a corner, right? So if we have an endpoint that's that's there, we can't know what's going on after it. So this is going. So G is also going to be differentiable on the open interval, right? And again, that's not earth-shattering, right? If that function f is continuous, you create a function that's continuous. We know that it's going to be differentiable unless there's a corner, right? A continuous function will be differentiable unless there's a corner. And are we expecting any corners when f is continuous like it is, right? Now, yeah, so when we get to the absolute value, which has that corner, it's continuous, we'll deal with that when we get there, right? But remember, we have that wonderful theorem that talked about the idea that if I do an integral, can I break it into different parts? So with the absolute value, I integrate from negative to 0, and then I go from 0 to positive, right? And if I do that, then I got rid of the corner, and then everything is good, right? So that's the cool thing about that. So even if there's a problem at 0, like with the absolute value, I can just break the integral up into different pieces, right? Okay? So then these two are, okay, great, wonderful. You're probably not really surprised by it. I mean, literally, it's like every theorem feels like it says it's continuous and on one interval and differentiable on another. Right? It just comes over and over again, right? The really important part is what happens if I do the derivative of this function? So if I created this function, drew its graph, and then did its derivative, right? Found the slope of the tangent line in all the different places, found its derivative, what would the derivative of it be? Well, it turns out that the derivative is going to be just f of x. So I've created this function that's generating all the areas, right? And then I plot those out, it makes a nice continuous differentiable function. And when I differentiate it, whenever I differentiate it as a particular value, it just gives me the original value of the function. Whoa.
So we did all that for nothing.
Well, no.
Yes,
Why?
because this is just what it was.
Wow.
Yes and no.
This is upside down.
I know. I can't figure out how to make the copier work anymore.
Nice.
I can't find antiderivatives and I can't make the copier work. It's like a
But
wizard.
which is more important?
At this point, I'd say the copier. Well, what was it? Brooke, you weren't the one with the physics. That was Aaron, wasn't it? Got all bent out of shape because it was upside down when he was doing the physics stuff. I still haven't figured out why it's a problem. Okay, so you should be like really. I mean, you shouldn't be reacting like this. I mean, this is very important. Okay, because here's what comes out of this, right? This is why I threw it. I asked Jackson I should wander you over here because I wrote this on the board over here. I put this up on the board. I said that f of x is an antiderivative of f if what? You take the derivative of that, you get back to the original function, right? Well, I just said that when I take the derivative of g, I get the original function. So what does that tell me about g? G has to be what? Derivative. Yeah. So in the end, when I do this integral, I get that g of x is equal to the big F of x, which is an antiderivative of f. Which is why when we go to find the second part of the fundamental theorem of calculus, now all of a sudden, why can I use an antiderivative to find the value of the integral? Because the integral is what? An antiderivative, right? So without this theorem, that whole thing, that all that nice, driving the car to Quick Trip thing doesn't exist, right?
We have to walk.
Well, yeah, well, you'd have to draw rectangles and then do all that forever and ever, yes? Right? Finding the limit of those Riemann sums. Anybody loving those, 21, 5, 2, they had to do 21, 20, 30, 19, whatever those were, right? I gave you 3 of them, and that's probably 3 more than you probably want to do, but you get like, no, this is actually pushing the car to Quick Trip. Walking there would be fine. You got Lauren sitting in the car, and you're pushing the car with Lauren in it to Quick Trip, right?
At least you can put it in neutral.
Oh yeah, except Lauren's one of those dumb people that just keeps putting her foot on the brake.
She's significantly clever. It's not
Oh, that's
really-
right, she's significantly clever, I forgot. You ever have that? Ever try to push somebody, help them get the car going? And they keep applying the brake because they're worried the car's going to go too far.
Yeah.
It's like, stop pushing the brake!
Yeah, it's like, you're trying to move the car. Why are you hitting brake?
All right. Luckily, we don't have that problem, right? Okay. So basically, so where does this go, right? I mean, it's like, okay, this is great. This allows me to find the value of that definite integral by using the antiderivative, right? Okay. Now, what they like to do is give you problems like this. This, if you started 5-3 at all, Brian, if you wandered into 5-3 at all, you know where it is, right? Come after 5-2 and right before 5-4.
Interesting. Didn't know that.
Okay. You're going to find problems. I think this starts with maybe like number 9, maybe number 7-ish in that assignment, right? So very early on, they're going to say, okay, use the fundamental theorem of calculus part 1 to find the derivative of each integral defined function below. A lot going on there, right? But first of all, do you believe that each one of these are integral defined functions? Is g of x defined as an integral? Is f of r defined as an integral?
Looks like it.
Is h of x defined as an integral?
Looks like
Yeah, so they are integral defined functions, right? And we just learned that as long as we have a function that's continuous on a closed interval, we can differentiate this, right? G of x will be differentiable. Yes, that integral defined function will be differentiable. Yes. Okay. So what they're asking us to do is not impossible. So how do I do that? So here is g of x is this integral right here. And I want to know what is g prime of x. Now, last year, I was really doubtful that this would show up on the AP exam because the short version of the test, you can't sneak this in here. But this is awesome for multiple choice questions, right? Because you get this, and you're like, how the heck do I know what this is? How do I find its derivative when I can't even do the integral, right? It's got t's in it. It's got an x in there. I can't it's like you're trying to do an antiderivative of it and plug in zeros and x's, and you're like, freaking out. Now, actually, you can do this. It turned out that on last year's AP exam, they actually gave you a problem where you could work backwards and do this. You could use the second part of the fundamental theorem of calculus to do the first part. Actually, if I really want to make you throw up and vomit, I can show you that problem from last year's AP exam. I actually, because they gave me all the AP exams, I did all the problems. So I got the actual questions. I did them all, and I looked at everybody's work, right? So like your buddies, Cake Girls, right? What was her name? Yeah, I actually looked at what they did on this exam, right? All right, now, this is a very easy problem, right? Because I told you in the fundamental theorem of calculus part 1 I told you that if we have a function that's defined in this way, then I know that g prime of x is just f of x, right? Now, what is f of x? F of x is the inside function here evaluated at what? Whatever this upper limit is, right? Okay, so that's a really important part of this, right? So if I want, so g prime of x is going to be this inside function evaluated at whatever that upper limit is, right? Okay, well, if you know that, then this becomes a much easier prospect, right? Because looking at this, you should be able to figure out that f of t is what? 1 over t squared plus 4. So if I want to find the derivative of g, I take that function and evaluate it for what? X. So what's it going to be? 1 over x squared plus 4. Done. You should be, this is the, James Franco, I got this. Right? It's like, this is like, whoa. It's like, I just made the Statue of Liberty disappear.
Really?
Yeah, also I think.
Your enthusiasm here is underwhelming at this point, right?
I'm sorry.
But-
I think I used all of it up in the first 5 minutes.
I do appreciate it. I did kind of need that to get going here, right? But that's it, right? I mean, what did I do? I took the function that is here and evaluated that and got this, right?
Awesome.
Okay.
Awesome.
Well, that means we should be able to do this. Now, here they're trying to be a little funny, right? They're using a big F out here. Because remember, this, when you do this integral defined function, you're really getting the antiderivative, right? They're like, let's be cute. Let's call it big F. Because what does big F represent? An antiderivative.
That's awesome.
But does it really matter in the context of the problem? No, what am I trying to find in this problem? I'm trying to find f prime of what? The derivative of this, so big F prime of r. What is that going to be? Well, it's going to be this function evaluated at what? R. So what's it going to be? It's going to be e to the 3r minus 1.
Nice.
Done. There is its derivative, yes?
That's easy.
Yep. Remember that when you get to those problems, right? And please remember that when you get to the AP exam. Okay? Well, I'm betting at this point, you can figure out this one here. This one here, we are trying to find h prime of x. And h prime of x is going to be what?
Cosine squared of x.
Boom.
Yay.
Okay? Feeling okay? How much time we got left?
Like half a mile.
Okay, cool. All right. Another way that I could do this, if I took this, instead of writing it like this, what if I just gave you the integral from pi over 2 to x of the cosine squared theta d theta? And again, the dummy variable doesn't matter as long as you're consistent. You don't want to mix the variables. Whatever you use here has to be here in the differential, right? Okay? And again, you're not exactly sure why there's a differential there, other than it's taking the place of the delta x from our Riemann sum, right? When we're doing our rectangles and triangles. Yep. All right. So what if I took this and said, okay, instead of doing this and finding h prime, what if I said do d dx of this? Do the derivative of that. What is the derivative of that?
Cosine
Squared of x. I'm just changing notation on you, right? I went from this notation, the prime notation, to the Leibniz notation. But it's still the derivative, right? And the derivative of it is still going to be the cosine squared of x. It's going to be this inside function evaluated at whatever this top limit is, right? Okay? Feeling okay with that? Again, it's a lot to throw you at 8:30 in the morning or 9 in the morning on Thursday, but again, Wednesday, yeah. It's like,
Yeah.
you guys are better off. You actually know what day it is, right? Yeah.
It's April 21st.
All right.
Holy cow, it is.
Oh, I know.
All right. So you have one more example here, right? So this time I'm doing it as a graph. I want to do this or do I want to do the other one?
Done in a month.
Yes.
Oh, geez, don't go there yet. Okay. Okay.
Wait, do we have anything to do after the AP exam?
Yeah, most of you are going to be trying to find a way to pass this class.
Ouch.
But that's the honest truth, right? I mean, some people will be trying to get their GPA to where they want it to be. Some of you literally will be retaking tests to get to the point where you'll pass the class, yes? Some of you will be taking tests for the first time.
Hey, we have longer. We have longer. We have till June.
Okay, so I mean, I can rip on just about everybody, right?
Because there's like,
Okay, except maybe Ryan and maybe Roxanne, but Roxanne's lab stuff was,
I got 48%.
yeah.
Yeah,
So it's like,
Nice.
it's like we're trying to fall off the train here a little bit, right? It's like,
A little.
so yeah, so we're going to spend the week out. Spend the week. I think I'm going to be gone the last 2 days of the week after the AP exam.
Why?
Because we got to give those people that took the AP exam chances to recover from the trauma of taking that test,
That's why
or
you're
to
gone.
create really good memes to put out on the internet. Yes.
Yep.
Okay. I want to look at this problem, but I think I want to look at another problem first instead. Okay. This might blow your mind a little too much for this morning, right? All right. So somewhere, maybe on the far back side, you've got a blank page, right? The whole back side is blank.
Should I
Yes.
make it upside down to make it consistent so it's not lonely? I'm gonna do that. Oh my gosh.
Okay, I just want you to write down the promise on the board. I want you to write down g of x is equal to the integral from 0 to x of 2t dt. Right? Okay, so you got that, yes? Okay. What I want you to understand is I said that g of x is an antiderivative of this function, right? So in this case, f of t is going to be equal to what? 2t, right? So therefore, what would be f of t, big F of t? What would be an antiderivative of this? I don't care, just give me a
B
antiderivative,
squared plus C.
okay? A antiderivative, just give me
B
one.
squared.
T squared, right? So f of t would be equal to t squared, right? Okay? So that means that if the fundamental theorem of calculus is really true, what should g of x be equal to? It should be equal to this evaluated at x, right? So this should be equal to x squared. So if I were to graph this and graph this, they should give me the identical thing, right? Okay? Because and again, don't get confused. This is technically not this is a definite integral, but it's not really because it's going from 0 to a variable, right? So this is really a function, right? It's not the same as if I'd gone over here and said, okay, let's go from 0 to 2 of 2t dt. If I do that, that's just a number, right? In fact, you do the antiderivative of this, which would be t squared. You evaluate it at 2, which would be 4. You do it at 0, 4 minus 0. The answer would be 4, right? I mean, I did that really quick, but I just need you to understand that this is not the same as this, right? But if you believe the fundamental theorem of calculus, part 1, these two have to be the same, right? Right? Are they the same?
Yeah.
Well, I can't do this on your graphing calculator, but I can do this in Desmos. Here it is. Yeah. Desmos allows you to graph an integral defined function. It literally says, okay, there's g of x equals the integral from 0 to x of 2t dt. And I can graph it. Boom. Wow, that looks really familiar. In fact, if I were to graph big F of x equals x squared, it is the same thing.
Whoa.
So is this integral from 0 to x giving me this antiderivative? Yeah. Now, your question, the question you should be asking, and Roxanne kind of got there, but didn't quite. Where does that constant thing come in, right?
Yeah.
Right? Where does this constant come in? So if this was x squared plus 1, what would that do to my graph?
Bring it up.
Bring it up 1. Well, that means that this graph would also have to go up by 1. So I could literally take this integral and do what? add 1 to it, right, and move it up. Now, we can also accomplish that by changing this limit of the integration a little bit. I'm not going to do that today because that's a little too much. But you can start to see that this will give me a specific antiderivative. But can I modify this to get all those other antiderivatives? Absolutely, right? Because all that's happening is if I shift this graph up, all I'm doing is adding extra area, right? Right? The area between the curve and the graph, I'm adding this constant area, yes? So if I have a plus 3, I just take this integral and move it up 3. I have some initial area already there. They love to do that on the AP test also, right? And I don't know when at some point you'll get to a problem like that. But most important, you get to see that this integral defined function is the antiderivative of what's inside there, right? That's the most critical part of it. And then from there, you can use the second part of it, which is how I can find any antiderivative. And the cool thing is, and I'm hoping you watched my first video, right, on the fundamental theorem of calculus part 2. 5.3 part 1. Did you watch the video? Okay. So, so put Brooke on the spot. During the video, Brooke, I believe I did the integral, did a definite integral using 2 different antiderivatives. Yeah, and when I did it with 2 different antiderivatives, basically I added a constant, right? I did 2 different antiderivatives. Did I get the same result? Just say, yes, Mr. Schultz, you did it brilliantly.
Yes.
Okay. So I did it, right? I'm a try guy now, right? I literally did it so you don't have to, right? You know the try guys, right?
Yeah.
Yeah. I did it so you don't have to. They would trip over the table too. That was maybe Zach. Zach's a try guy, yes?
Zach?
Yeah.
Yeah, I tried plenty of things.
That's awesome.
I tried spacing out this class, it's not worth it.
No, there is a try guy who is named Zach.
What's the other guy's name?
Oh, there's I haven't watched him for a while. There's a guy that drinks all the time. What is his name? He's probably the best cook of the bunch.
The cook?
Yeah.
He cooks them?
Well, yeah, they have accounts. Like they'll give them all the ingredients to make an apple pie, but no direction how to do it, and they have to make one, right? Or they'll literally say, "Make this," and they won't give them anything except here, stop, make it, right? And they do it, right?
That's awesome.
Yeah. Yeah. Eugene, that's his name. Eugene, which is I can't remember which locker it was. Remember that he actually, I did on a video. They met at an award show, I think it was. Eugene from the Try Guys.
Nice.
It was either Cora or what was his sister's name? I can't remember.
Dave?
Yeah. What was anyway, so Eugene is one of my favorite. Is my favorite Try Guy. Except he tends to he plays the guy that drinks all the time. You know, that's an old skit going back to like 50s comedy.
Yeah.
He pretends to be drunk all the time.
That's awesome.
Yeah. Eugene's just taking it to a more modern kind of. Hey, I don't know. I haven't seen Try Guy videos since all COVID stuff started, but
What?
because they haven't been out doing a lot of videos because of the quarantine.
I need more graphics.
They can do
More graphics.
quarantine.
The bad news is that today being Wednesday,
Yep.
I need to get you going on 5-4 one way or the other. So I'm debating on whether if my videos are somewhat decent for 5-4 and they're not dated, like I don't make references to Hannah nodding off in the back or something. in the videos. Probably a little bit of both, right?
Yeah, or drawing carefully.
Yeah. I may just have you watch I may just post the 5-4 videos just to get started. But this we need to do kind of in person because it makes a little more sense if you're getting the live show to it.
I like the videos.
Well, last year's videos of this exact same thing is on the classroom page also.
I think you should do that for next year. You should just film all of the sections.
Well, at the rate I'm going, I will have videos for all of it at some point.
And then you can just post them all and then go over what you need to a person. And then you can